fresher Shrenik, you can just intimate me that there is someone who is trying to attend, trying to get in the meeting. So I'll allow the person. The most important thing that I want to disclose here that due to some technical issues with the university and the Google G Suite, there is no recording facility as of now. So the lectures that I'll be giving will not be recorded. So I cannot give you any recording afterwards. At least this I don't know how long this problem will persist. So what I'll do, I'll try to write down as many equations, as many notes as possible on the whiteboard, and you may either take a screenshot of that, or I can share the note from the whiteboard to you. Or if possible, I'll share some scanned copy as well, but that will not regularly, but intermittently. Say in 2 weeks time, or once I cover up a particular topic, then I'll share the notes on that particular topic. So is there any alternate arrangement that you can make? That do you have any facility of recording the classes? Is it
Yes,
possible
sir.
from your side?
I record for myself, so I can share with my classmates.
But using anyone can do, but screen recorder means your entire screen will be recorded with audio, right?
Yes, sir.
Okay, so I'll request at least, since both the meetings are happening simultaneously, so one of you can take the uh, arrange or make the arrangement to record the class and share with all of your friends. Okay, then as long as this facility is not available with my side, from my side, I'll request you to just continue with that. So today's class, we will be recording today's class.
So I'm recording.
Okay, so Himesh is recording today's class. Okay, so Himesh will share the recordings with you. So Himesh, you tell me whenever ready, I'll start the class then.
Yes, I've started the recording.
Okay, thank you. So the subject that we'll be discussing in this session, or this in this course, is basically signals and systems, and I will be taking the systems part. Okay, so I will be discussing about systems. So before I start discussing about the systems, so the first thing that will come into the mind is the definition, or how do you define a system, or rather, without going into much technicality, if I ask any one of you that what do you mean when you hear the term system? What do you mean, or what do you understand by the term system? Can anyone from section A tell me? Yes,
So
sorry.
the space in the environment that we want to analyze, or that is of our interest.
Any space, anything. Okay, so Shorij is saying that the space that we want to analyze, that is of interest, that can be termed as a system. Okay, anybody from section B? Any idea?
স্যার
Yes.
স্যার সিস্টেম মানে স্যার মানে যেখানে হচ্ছে যদি এক রকমের সিগন্যাল যদি দিই সিস্টেমে তাহলে হচ্ছে আউটপুট হিসেবে আরেক রকমের সিগন্যাল পাবো জেনারেট হবে
সিস্টেম বলবে ঠিক আছে okay so Saptoshi is saying that for a system can be defined as something when excited by a type of signal it will generate an response. Okay.
ইয়েস স্যার
Right. If from a very layman's point of view, system is something which, when excited, will give you a response. Or if we go by the definition given by the Shoris as well, says anything that we want to analyze or that is of interest to us can be termed as a system. Both of you are correct from your respective viewpoint, because system is a very global term. Okay, system is a very global term, and if I say in a single word, it basically encompasses anything under the sun. So anything you can think of, you can think of it as a system. Now, since we are engineers, we should be more concentrated on the engineering aspect of the system. Okay, so from engineering aspect of the system, there should be some formal definitions of the system. So now, keeping in mind that it's a very global term and anything under the sun can be regarded as a system, even not under the sun, anything in the universe. The solar system is also a system that operates. Okay, but the only contradiction that I'll right away put that in some situations the systems are spontaneous. Even without some excitation, any excitation, it might produce some output spontaneously. This is also system. Then we have inert systems where you even if you put some excitation, it may not give you any visual or distinctive result or response, but still that's a system. So it's very confusing. So without indulging into the confusion of globalizing the term system, we should be concentrating on the very definition of the system that should be applicable from an engineering point of view. And this field of engineering is normally termed as systems engineering. Okay, which will later on, as you will go on in your courses, will converge to control system engineering or any other engineering also. The systems, the basic definition of system is very important. So if I want to define a system, one definition may be a system is a quantitative description of a physical process. Now, key term is a physical process because we're looking from a system engineering point of view. So, from engineering point of view, we can only deal with physical quantities. So, system is a quantitative description, not qualitative. It's a quantitative description of a physical process which transforms signals, that is signals at sorry its input to signals at its output. So it's a quantitative description of a physical process that transforms the input signals to output signals. It is more or less conforming to the word definition I think Supratim gave from section B, right? From an analytical perspective, if I look from an analytical perspective or from a mathematical perspective, uh, system is a black box. It can be termed as a black box from a mathematical abstraction point of view. Okay, that deterministically transforms input signals into output signals. So this deterministically transform means you can define this transformation in terms of some deterministic mathematical expressions. Then also you can define that as a system. Now I have used the term black box because we will let us see that this mathematical expression or these transformations that takes place from input side to output side may not be very localized one or may not be restricted to a particular class of system, particular system. It rather it will represent a class of systems. That's why a black box model is sometimes used to represent the system. So these are some formal definitions of a system. Okay. Now, since Again, I'm coming back to the fact that we're from looking from engineering point of view or from a system engineer's point of view. So from that respect, these are the two definitions, okay, that we should look forward to. Now, if I elaborate further, we can write in the third point, a system is a set of either interacting and or independent components, or rather component parts forming a complex. I'm using the term complex. I may not be very complex or intricate. Sorry for this writing. So it's basically, it may be a complex or intricate composition that comprises of different component parts. Those component parts may be interacting or and they may be independent. So this is a more physical definition of a system from the physical component point of view.
Sir, what is meant by
Now,
it?
what is meant by
Intricate?
intricate? Means, see, complex means it is very difficult to analyze. It comprises of very complex mechanisms, interlaced mechanisms. Intricate means it's very fine, it's very detailed. Okay, it's very fine. Intricate means you can say it's very fine, not very complex, but very fine. Or some delicate interactions is there. Okay, that is simple, but it's very well defined and very fine interactions. Okay,
Easy to explain the
yes. It's easy to explain, but it is very, very important that you maintain that interaction.
Okay, sir.
Now, next, once I've defined this sort of systems, then there are certain properties of a system that you should keep in mind, that every system, number one, is delineated by its spatial and temporal boundaries. Delineated there means clearly demarked by their spatial space, the boundaries on space, how much space they occupy, or their temporal behavior, temporal boundary. Temporal boundary means a particular system may exist only during a particular time frame, and beyond that, that particular operation or system may not actually exist. So this temporal, okay, the system will exist, but that particular operation may not exist. So every system will be clearly demarked by their spatial boundary and their temporal behavior, if any. If a system has a property that its operation changes over time, during a particular time frame, it functions in a particular way, and in other time frame, it functions in a completely different way. So these functions, so these operations should be demarcated by these temporal boundaries, right? As soon as you put out these boundaries, so the system outside the boundary, they are surrounded and influenced by its environment. That is, anything beyond the system boundary will be termed as the environment for the system. So the environment will surround the system and it will influence the system in different ways, right? So this is how the boundary of a system can be defined. Third, any system will be described by its structure and purpose, that how it is made up and what purpose does it serve. So this will describe any particular system, and they'll be expressed in its functioning. That is how the purpose is served by which functions, or how this system functions. That is the expression, how they are expressed. So it is described by structure, whether it's a mechanical system, whether it's electronic system, whether it's a hydraulic system. Then purpose, it's a, say it's a lever, it's a something lifting system, it's used for lifting, and then express its functioning, how the lifting operation is being carried out, which of the methods are used. So this is how it functions. So any system will be demarcated by its spatial and temporal boundaries, and outside this boundary it will be surrounded and influenced by environment. Now given a system, it will be described by its structure and the purpose, and it will be expressed in its functioning, right? So in a summary, in this course, we will be concerned about physical systems. And physical system is nothing but a collection of physical objects. Those are connected together to serve a particular objective. Now, the example of physical systems may be cited from, say, your laboratories, industrial plant, or any utility services that you see. And it can range from a very simple system, such as like a safety pin, to a very complicated satellite that orbits the Earth. So anything can be described or defined as a system or a physical system, whichever you can express, or whichever you can, which is having a physical form, that can be termed as a physical system. But as I've already mentioned, the term system is very global.
So is the boundaries always be real or it can be imaginary?
Obviously real. How physical boundary cannot be imaginary. Okay, but
Yes, sir.
since the boundary may vary, boundaries may vary, but it should be always real. So for physical systems, I'm talking about all these things are physical systems, and there are some other systems. Since system is a very global term that you can term as a non-physical system, or from a more general perspective, the term system can be used to describe a combination of say components or functioning that are not all physical. Like if I term them as non-physical system, the examples will be economical system,
Operating system.
yes, academic system, anything, social system, academic system, right? See, these systems basically do not have any physical existence, but for the functioning of these systems, we need some physical quantities, and to evaluate such systems, we have some certain parameters, right? Like the economical systems. In our economical system, it is governed by the currency. And to represent the currencies, we have different currency notes. But most of the economic operations are based on policies, right? Whatever economical growth or economical ups and downs that are happening based on policies. So these policies are basically, they do not exist. But when you are applying these policies, then some of the parameters of these economical systems are varying. And these variations are demarcated by this parameters, by these signals, that the currencies, how the Indian currency is changing with respect to other dollar value, like that. So these are the signals. These are the signals, and the actual system, or the actual system operation that is happening, it is not merely physical. Similarly, in social systems, some of the output or the responses that you can see are physically uh, visualized, but the actual system that takes place is entirely non-physical. Similarly, for academic purposes, right now I'm giving you a lecture. You are absorbing some information. You try to recollect that information, and in a process of evaluation, you put that information into paper. I'll put some marks on that, and that marks and numbers will be the output of the system, and based on that, we'll try to improve the system, right? From your side also, and from our side also. So this set of systems are basically non-physical type of systems. So whenever we're talking about systems, from engineering point of view, we shall consider only physical systems, but from a global point of view, it can be non-physical as well. In fact, you'll find that a lot of your seniors, those who have passed engineering, they have joined some financial firms, okay, because the tools they use, okay, that may incorporate some of the skills, soft skills, okay, and that again is very much non-physical, but the tools are physical. So interactions is happening through physical entities, but the actual operation is non-physical. So this is how the overall system is non-physical, because some of the components are physical, but mostly they're non-physical. So anything under the sun can be clustered into different systems, right? If you go through, I'll just make one observation that in some cases, in some of the books, in systems theory, you'll encounter the term system, but later on, you encounter the term like plant or process. These are the different definitions given to physical systems. Okay. So normally plant represents a physical component like machines, heavy machinery, heavy tools. Whenever you are describing a physical machinery or physical something that physically operates something, you call that a plant. But what is process then? Process is basically some operation. If you want to describe some operation, we normally term that as a process. Okay, like it's mixing. It is mixing to say two different components has been mixed using a stirrer. So that mixing is a process. In a manufacturing unit, we manufacture different products. So it flows like a group of blockchains. Like in one sector, some product is made. In the next sector, it is being packed. And the final sector, the stamping is done. In the final sector, it is being packed in a big box for transportation. So this sequence of operation that follows one after another will be termed as a process. But in each sector, the production, it involves some machinery. So there is a small production plant. Then there will be bottling or packing plant. That is a plant. Then there will be another packing plant for the transportation. So there's another plant. But the operation that interacts, or the interaction between these plants, is referred to as a process. So this is again a system, but it is a subset of the system, right? Plant is a very specific physical system, and process is a very specific operation, which comprises a system, right? Like a manufacturing system. The manufacturing systems are defined by a process. That's why you call it a manufacturing process. There are different systems, there are interactions between them, and then we define it as a process because the system are in cascade and they operate in a sequential manner or a follow a particular pattern. So this following of a particular sequence is termed as a process. So I just do not get confused about that, but these are subset of systems. So we will not indulge into much into that, but I just wanted to make this point because in some of the textbooks you will find that it is sometimes termed as plant, sometimes as process. So they are basically a subset of this system. And system is the most global part, the global term. Next comes classification of systems. Okay, the first classification, I'll just put one after another. First classification, continuous time versus discrete time. That is continuous time system versus discrete time system. Now, what is a continuous time system and what is a discrete time system? Now, this is the simplest classification to understand because the idea of the discrete time and the continuous time system is one of the most fundamental properties of the system, and it is referred to the signals, okay, associated with the systems. If in a given system the input and output signals are all continuous, that means it is continuous in time, then we call that a continuous time system. But when the input and output signals are discrete in time, then we call it a discrete time system. How? Suppose we don't know what is there. We have a system, there will be two situations. First, you have input and you have output. Now the input is such that it is defined as this. See, for each and every value of t, there is a value of xt. And the corresponding output is also continuous. Then we call this type of system as a continuous time system. But what happens if the system given to input, is discrete? Like they exist only at discrete instants of time, and then the output of the system will also be discrete. So the blue one, in those cases, the blue one will be called a discrete time system, and the red one will be termed as a continuous time system, right? Depending upon the signals associated with the input and output of the system. So this is a very clear-cut distinction. But there is another type of system which is very interesting, which is called a hybrid type of system. There is given a continuous system, the output may be discrete or discontinuous. And given a discrete time system, the output may be continuous. So in those systems, it is termed as a hybrid type of system. Now,
স্যার এটা
if you
এক্সাম্পল মাইক্রোফোন হতে পারে,
huh?
এটার এক্সাম্পল স্যার মাইক্রোফোন হতে পারে হাইব্রিড সিস্টেমে, কারণ মাইক্রোফোনে স্যার আমরা
আমি বলে বুঝতে পারলাম না কি বলছো, মাইক্রোফোন?
ইয়েস স্যার
Yes. No, there may be two types of microphones. If you are using an analog amplifier, okay, or analog receiver,
sir.
and recording in analog recorder, then it will be completely analog to analog. But if you are recording in a digital platform, then it has to be discretized.
ইয়েস স্যার
Okay, I was coming to this point. Now, this system, internal to this system, there will be different types of signals flowing through. Now, whenever I'm making the point that it's a continuous time system, because given a continuous time input, the output is continuous, that is okay. It's a continuous time system, you can term it. But it may happen that intermediate signal or within the system, there are certain positions in the system or portions in the system where there are some discrete signals available. The example will be a computer control system or anything that is utilizes a digital computer or a microprocessor. Okay, so in those situations, what it will do, it will accept continuous time signal and convert them to a digital signal by ADC, and then perform some operation in digital domain, and then reconvert that signal to analog by DAC converter and give you output in a continuous time again. So from input output point of view, it may look like a continuous time signal, but basically it's a hybrid system because in between there is a discretization happening. Same thing can happen. A system may accept discrete time signal, convert it to analog signal, then some analog portion is there which operates the analog. Um, some pneumatic valve is there, suppose, and output of the valve is then discretized to obtain the discrete time signal. So hybrid system is the most common form. But if you can find out some system which accepts continuous time signal and gives you continuous time output, then it's a continuous time system. And if you ask me, most of the systems that we normally experience are basically continuous time systems in physical systems. But whenever we implement, whenever we try to modify some system, we generally now involve some discretization, either digital computer or microprocessor. As soon as these synthetic things are incorporated, then it becomes a discrete time system. Obviously, there are some natural processes which are also in discrete in nature, like some of the events in environmental events that is happening, like say thunder showers or some rainfall, okay, and snowfall. These are discrete events. When you are modeling an environmental system or a weather system, then these events are discrete time systems. But in general, whenever suppose when you're experiencing daily life different situations, normally they are continuous time. But whenever you're using some gadgets nowadays, that basically mostly are discrete time system. But they can accept continuous time signals. That's why this classification of continuous time and discrete time systems are nowadays more or less replaced by these hybrid systems, right? It's very difficult from analysis point of view. Whenever you are designing a system or analyzing a system, you'll find that it can either be analyzed from continuous time point of view, assuming that all operations are happening continuously, which is mostly the case of physical systems, in natural physical systems. And whenever you're trying to modify that, you normally now incorporate digital computers or microprocessors, thus making it a hybrid system. Although all the operations are happening continuously, but you are controlling it intermittently using a microprocessor or a digital computer. So it's becoming rather a hybrid system. And there may be purely discrete time system. Obviously, there are situations in electronics we find purely discrete time systems. Whatever happens within a computer are purely discrete time system. There is no analog signal there, right? So all the registers, they're getting updated. This is a typical example of a pure discrete time system, right?
So,
So
sir,
yes.
can we call all the digital signals are discrete time signal, but all discrete time signal is not the digital signals?
There is a very classical difference between this digital signals and discrete time signals. Okay, see, discrete time signal means it exists in this different values, but in digital systems, whenever you're storing a system data, you can store the data like this. Like these are
Okay.
the stems that you have, suppose, but in between you can store the data. Sorry, so this is the data you have, but this data is available throughout this period. But in discrete time system, this data is only available at these intervals, right?
So,
But
sir, it's
if you
more
store
quantized.
them in digital computer, normally you store the data, so
Yes, sir.
it remains there. But this data is a quantized value. It can only assume this discrete values, right? Unlike
Yes, sir.
continuous time signal. In continuous time signal, it can assume any finite value between these two. And then maybe if you go for infinitesimal increment in time, you can find infinitesimal increment in value as well. Right? You can divide this any sector in infinite small. You go for picosecond, nanosecond, you will get small and small defined values, right? But in discrete time systems, they're either discrete events or they're quantized. Their values are fixed, like this. So this will be held
So, sir,
constant.
how do we differentiate between such instruments which uses continuous time or
Ah,
discrete
yes,
time?
you can see some analog instruments in your laboratories. You see, suppose given some voltmeter or ammeter, there are some voltmeter or ammeters which are called analog, where there is a deflecting needle, right, which deflects as long as there is a current flowing. So for ammeter, or as long as there's a voltage appearing across the terminals, it will get deflected. And this deflection, it will not move from 0 to 5 volt instantaneously. It will go through 0, 1, 2, 3, 4, 5, and any change in value will correspondingly make the needle to move smoothly from one value to other. So it will encompass all the values. But if you apply a digital multimeter, then you'll see it will move from 0 to 5 directly. It will not go through 1, 2, 3, 4, 5 or in between. It will move from 0 to 5. There's a discrete jump from the value of 0 to 5, right? The difference, have you got my point?
Yes, sir. Yes.
So in analog instruments, you can clearly see that values are changing throughout the range. From 0 to 5, it is encompassing all the values from 0 to 5. But in discrete case, it will jump from 0 to 5 directly. Right? Okay, so this is one classification. I guess let us move on.
Sir, could you give a few more examples about hybrid systems?
Okay, any hybrid system means suppose when you are actually measuring an analog voltage using a digital multimeter, that's a typical example of a hybrid system. Because even if you change the signal that you are giving is analog signal, right? If you change the analog value, the change will be accepted by
So,
the meter and it will show you the quantized values only.
so DAC converter and ADC converter.
Yes, I already mentioned DSC, ADC converters are there.
Sir, can sampler be termed as a hybrid system? Because it converts continuous to discrete time system.
It is not actually a system. Okay, if you term that as system, because sampler, continuous time system, if you sample the values, you'll get things. Okay, if you term it as a system, uh, I'm not sure whether it can be termed as a hybrid system, because what it does, it samples a particular value and waits for the next time instant. Okay,
Yes,
so
sir.
that value may be discrete value, maybe digital value. Okay, in a sense, we can say that it's some operation that converts a continuous time signal into a signal of discrete intervals. Okay, yes, that is
Sir,
again a type of operation.
the mechanism by which we generate clock pulses, can that also be a hybrid system?
Yes, 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 yes. Okay, so there will be plenty of examples like the analog integrators that you use using the op amps, purely analog, right? So whenever you're using that in a stable multivibrator or any other electronic form which generates pulses, so it is basically converting the analog thing, analog equipment. If you're using the analog equipment to generate some discrete signals, so there will be different examples. Okay. So let us now move on to the next classification, linear and non-linear. So this is again a very important classification, and this basically divides the entire system engineering into two parts. Continuous time and discrete time is one section. Linear, non-linear is another type of classification. Now, how do you define a linear system? A linear system obeys the properties of scaling, that is homogeneity and superposition. And that is called the additivity. While the nonlinear system does not obey at least one of these. Right? It may obey one of them, or it may not obey any one of them. That's a nonlinear system. So any system that doesn't follow this scaling or superposition property, either of them or both of them, is a nonlinear system. So what does this? I think you know what is the scaling property or this homogeneity property.
The scaling means if we multiply the input by some scalar, then we will get output multiplied by that much scalar
Yes,
quantity.
yes. Suppose.
So we can also say that we are changing the input and the output by some factor.
Yes, that is another. Wait. Suppose you have a system H. Okay, so if we apply a input K of ft is the input, then the output will be K of hft. So this is the scaling property. If you multiply the input by K, then output will be multiplied by K with respect to the original signal. Simple as that. And what about the superposition?
So if you add some value with as an input, then you will also get the value as an output. I want to say that if you add alpha as an input, then you will also get the alpha plus adding value as output.
No, suppose we have two inputs h of f1t plus f2t. So it will be basically h of f1t plus h of f2t, right? That is, if we apply f1t, we get this. If apply f2t input, the output is this. If we apply f1 plus f2, then the output will be h of f1 plus h of f2. That is
Yes, sir.
additivity. Now these two can be clustered together like h of, sorry,
Sir, in this case, the F1 and
yes,
F2T both signals are independent, are they?
yes, independent. So if you just add these two formulas together, then you can write this. Right? Given an input k1 f1 plus k2 f2, the output will be k1 hf1t plus k2 hf2t. And this is the property that any linear system will satisfy. Right? Now the third important property. Okay, let us move on. Time invariant versus time varying. Now, what does it mean? A time invariant system is one. The time invariant system is one that doesn't depend. The response doesn't depend upon when the input is given. Whenever you give the input, the nature of the output will remain same. Whereas for time varying system, depending upon the instant at which you are giving the input, the output will change. Or in other words, in terms of mathematics, you can write if input ft gives you an output, sorry, h of ft, say which is termed as yt, then the input f of a delayed input f of t minus capital T, that will be h of f of t minus capital T, will yield output. Then it's a time invariant system, right? So yt, the nature will remain same, but it will just be shifted like this. And if this property is not satisfied, then it's a time varying system. I'll give you an example. Suppose if you given excitation that I'm drawing the red, at this point I'm giving an excitation from 0 to the particular value, and the corresponding output is suppose this. This is the output. Now if I shift the excitation from here to here, the output nature will not change. Sorry, just the same.
So the second wave is the output of the first signal.
Green one is the output and red one is the input, the step input like. So at the first case, I've given input at t equal to 0. Now I have the given input at t equal to capital T. So output nature remains same. It's a time invariant system. But for time varying system, it may happen that for this case, suppose the output was, I'll draw like a different way. In this case, the output was like this. But in this case, the output may become like this. So it's a time varying system. Depending upon the instant at which you're exciting, the nature of the response will change. Say in this first case, it is yt, but in next case, it is not yt minus t, it is y1 t minus capital T, which is not equal to some completely different nature of the response. See the green one, if you look at the green one, both of them are same, but the blue one, the nature is completely different because the time varying systems, it's the parameters are basically time varying. So at t equal to 0, what are the parameter values? At t equal to capital T, the parameter values of the time varying system has now changed. So the response will be completely different as compared to the input given at t equal to 0.
Sir,
But in time invariant case, the time parameters are always fixed, they're not changing. Yes?
sir, can you explain the graph? I am not able to link it with the equations.
These equations.
Yes, sir. I am not able to link the graphical response with the equations that you have written above.
Okay. I got it. Suppose in first case, the input is given here. Okay, let me draw the input in a bigger one. You're given a step input. So if it's a time invariant case, the output was like this. This was the output. So this equation is say yt, right? Some equation. I'm not writing the equation. Now, if you change the instant of this input instead of this, at this point, what will happen? This nature of the yt will be maintained and it will start instead of from this, it will start from here and the same nature will be followed. And the equation will remain to be yt. Whatever, say it is 1 minus e to the power minus t by, say, capital TC, time constant. So nature will remain same in both the cases because it's a time invariant system, right? But in time varying case, suppose at this input at t equal to 0, the output was, suppose yt is this. But if you put the input at t equal to capital T, the output equation will not change. 2tc. So it will become sluggish. Right? What happened? The time constant has now changed, right?
Yes, sir.
The dynamics has now changed. Right?
Yes, sir. Yes.
The blue one is not a time invariant one, it's a time varying one. But because the response changes from this to this, because we have delayed the input by capital T. But if the response equation remains unaltered, and it is irrespective of the time instant at which you excite the system, it's a time invariant system. Right?
Yes, sir.
Now, this will be clear when I will discuss about the modeling. Then it will be clear. Okay.
Clear, sir.
Okay. Next classification is a bit technical one. Causal versus
So one of our classmates wants to join.
yes, thank you. So next classification is causal versus non-causal. So what is a causal system? A causal system is basically non-anticipative. That means the output depends on current and past inputs. But in case of a non-causal, the output depends on future inputs. Right? So as the future input is not physically present at the current instant, obviously you can say that all the real-time systems that we face are basically causal system, right? Because they cannot have the future inputs available to them, right? Because we know it's a cause-effect relationship for a given system. Given an excitation, it will produce an output. It cannot anticipate the future input and act accordingly. So most of the real-time systems that we face will be, almost now all the real-time systems that we will face will be causal. Understood?
Sir,
Then, Bolo,
if there is a feedback, then is that causal or non-causal?
if there is a
Feedback somehow.
feedback means
Feedback.
feedback. No, it's obviously causal. Feedback means your output information is updated and then it is being feedback. You cannot anticipate what the output will be. Okay, it's obviously causal.
But sir, if the feedback of some future value is required to get the output, then it will become non-causal then.
How can you get the future value of feedback? Suppose at time,
No, sir, then it will not remain a physical system then.
okay, so now that's the question I was asking, as I want to ask that. So causal systems, all the real-time systems are causal systems because it follows the cause-effect relationship. Then why do we define a non-causal system? Is there any existence of a non-causal system? Or can we define a non-causal system where the output will be a function of future input? Can anyone?
Sir, I think there is no existence of non-causal system because we cannot predict input values beforehand. So non-causal system is not possible to exist.
স্যার যদি কোনো একটা সিস্টেম নিয়ে আমরা ধরুন প্রিভিয়াসলি কাজ করে থাকি, তাহলে সেই সিস্টেমের ইনপুট আউটপুটের একটা রিলেশন আমরা পাবো টাইমের উপর বেস করে। তো আবার আবার যখন কারেন্টে আমরা যখন সিস্টেমটাকে রান করছি, তখন এট দ্য পয়েন্ট অফ টাইম আমরা যে ইনপুটটা দিচ্ছি তার এস্টিমেটেড ভ্যালু আমাদের একটা আগে রয়েছে, আগের যখন এক্সপেরিমেন্টটা করেছিলাম সেই হিসেবে কি বলতে পারি?
Okay, fine. এটা বলতে পারি, but the problem is that you do not know that in each of the runs you will go through the same set of result or same set of data. If you can ensure the consistency, then you can ensure that okay, we have this past data and we know after this set of operations we will achieve at this data. So even if we achieve that, you can use that data. I'll give you
periodic function use করা যায় না মানে
বলো
আর ফিউচার periodic use করব
করে কি করবে, সেটা কিভাবে করবে?
সো মানে তো প্রেডিক্টেড থাকে যে টাইমের পরে আমি মানে
হ্যাঁ, এবার তুমি কি করে এনশিওর করবে যে ওটা একটা পিরিয়ডিকই ফলো করবে? তুমি এনশিওর করবে কি যদি কোনো কিছু ডিস্টারবেন্স এসে কিংবা সিস্টেমের রেসপন্স যে পিরিয়ডিকই থাকবে, সেটা তুমি কি করে বলবে? তাহলে হবে না। হ্যাঁ, তুমি যদি জানো যে আউটপুটটা একটা সাইনোসয়েডাল ইনপুট আছে, একটা সাইনোসয়েড ওয়েভ আছে, সাইনোসয়েড ওয়েভ জেনারেটর পাচ্ছ, তাহলে তুমি বলতে পারো ওকে এর আউটপুটটা সবসময় সাইনোসয়েড থাকবে। কিন্তু তুমি একটা ফিজিক্যাল সিস্টেম নিয়ে অপারেট করছো, ওটা ইনপুট দিয়েছো, হ্যাঁ, এবার তার ফিউচার ইনপুটটা কি আসবে? তুমি ফিডব্যাকের ক্ষেত্রে ওই আগে যেটা বললে যে তুমি এটা ফিউচার আউটপুট জানো, তখন তুমি ফিডব্যাকে সেই আউটপুটটা নিতে পারবে, কিন্তু ফিউচার ইনপুটটা কি করে তুমি জানবে? ইনপুটটা তো তোমার হাতে নাও থাকতে পারে সবসময়। ইনপুটটা তো পুরোপুরি এক্সোজেনিয়াস সিগন্যাল। ফিডব্যাকের ক্ষেত্রে ফিডব্যাক সিগন্যালটা তোমার হাতে থাকতে পারে, তুমি ইনপুটটা কখন কি চেঞ্জ করবে তুমি বুঝবে কি করে? মানে এখানে অনেক রকমের প্রশ্ন থাকতে পারে। আমি একটা এক্সাম্পল দিয়ে দেখো, এটা হয়তো তুমি বুঝতে পারবে। একজনরা ঠিক বলেছিল যে এটা রেকর্ডিং যদি যেটা থাকে আমার কাছে তাহলে আমি করতে পারি। আমাদের আসল প্রবলেমটা কি, আমরা যেখানে আমরা সবাই আটকে যাচ্ছি সেটা হচ্ছে আমাদের সবাই টাইম ফ্রেমে ভাবছি। টাইম ফ্রেমে ভাবলে কিন্তু পাবে না, টাইম ফ্রেমে সবকিছু কজাল, নন কজাল তুমি রিয়েলাইজ করতে পারবে না। তোমাকে ভেবে ভাবতে হবে টাইম ছেড়ে
ফ্রিকোয়েন্সি ফ্রেমে স্যার,
স্পেশাল ডোমেনে।
ইয়েস, ইন দ্য সেন্স হ্যাঁ, এবার আমি খুব কমপ্লিকেট করছি না ব্যাপারটা। ধরো এটা একটা ইমেজ আছে, খুব একটা হেজি ইমেজ আছে, ঠিক আছে, কিংবা একটা ইমেজ আছে, সেই ইমেজটাকে তোমাকে তার ফিচার গুলো এক্সট্রাক্ট করতে হবে, কোথায় কোথায় কি ফিচার আছে। নর্মালি কি করা হয়, এটা ধরো 0 পয়েন্ট, আর এখানে ধরো এক্সট্রা 0 আর 256, এখানে হচ্ছে পিক্সেলস গুলো আছে, ঠিক আছে। আমরা নর্মালি করে কি এখানটা অ্যাক্সেস ধরে নিই, এইটাকে একদম 0 থেকে শুরু করে 256 অব্দি নিয়ে যাই, ঠিক আছে। নিয়ে আমার ফিগারটাকে স্ক্যান করতে করতে যাচ্ছিলাম। এবার তুমি ধরো এখানে দেখলে যে একটা গ্রাফ আছে, গ্রাফে তুমি 2টো পয়েন্ট স্ক্যান করেছে এই অব্দি, ঠিক আছে। কিংবা তোমার কাছে এই ডিস্ট্রিক্ট পয়েন্ট গুলো আছে, তোমার কাছে জয়েন করতে হবে। তুমি আবার 3টে পয়েন্ট আছে, জয়েন করতে হবে। তুমি লাইনটা এদিক দিয়ে সরি এইভাবে ঘুরিয়ে নিয়ে যাবে না এইভাবে ঘুরিয়ে নিয়ে যাবে, তুমি বুঝবে কি করে? তখন তুমি করলে কি, যেহেতু ইমেজটা তোমার কাছে অ্যাভেলেবল, ঠিক আছে, তোমার ইউ হ্যাভ দিস ইমেজ, ইউ মুভ অন বিয়ন্ড দিস পিক্সেল। ধরো এখন তুমি আছো 5, এটা হচ্ছে সরি 05 পয়েন্টে আছো, এটা অ্যাক্সিসে 0, এটা 5, আর এটার এক্স অ্যাক্সিসে 5। তুমি যে কোনো এই লাইন বরাবর গিয়ে 7 নম্বর হরিজন্টাল 7 নম্বর পিক্সেলে কি আছে সেটা তুমি রিড করলে, কারণ তোমার ডেটা সবসময় আছে, তুমি জানো এটা পিক্সেলের রেফারেন্সে সরালে না, রিড করে এই ডেটাটা নিয়ে দেখলে এই 7 নম্বরের পয়েন্টটা আমার এইখানে আছে, তাহলে আমি যদি এইদিকে এগোই তাহলে কখনো এটা এক্সট্রাপোলেটটা ম্যাচ করবে না। তখন তুমি 6 চলে এলে, 6টা রিড করলে, করে দেখলে হ্যাঁ এটা এখানে আছে, সো ইওর এক্সট্রাপোলেশন শুড বি লাইক দিস, নট দিস। এইভাবে তুমি একটা ফিউচার রেফারেন্সের ভ্যালু 5 নম্বর লোকেশনে থেকে 6-7টা রিড করে এসে 4-এরটা 5-এ কি করে কানেক্ট করবে সেটা তুমি এক্সট্রাপোলেট করবে, সেটা ডিটারমিন করতে পারবে। সো দিস ইজ কাইন্ড অফ এ নন কজাল অপারেশন, কারণ তোমার 5-এ থাকাকালীন অল ডেটা দ্যাট ইউ হ্যাভ ইজ আপ টু 0 to 5, আর তুমি 6-এর সাথে গিয়ে একবার দেখিয়ে, কারণ ডেটাগুলো তোমার কাছে অ্যাভেলেবল, তুমি ফ্রেম অফ রেফারেন্স চেঞ্জ করলে না, জাস্ট একটা ডেটা, জাস্ট দেখে এলে, দেখে তাহলে ওই রেফারেন্সটা তুমি পেয়ে গেলে, তারপর তুমি এটাকে এক্সট্রাপোলেট করলে, করে এবার তুমি এটাকে অ্যাক্সিসটাকে মুভ করো, 6 পজিশনে এসো, তারপর 7 এসো, এবার তুমি অপারেশনটা করতে থাকো। তাহলে আমার এখানে ইন্ডিপেন্ডেন্ট ভেরিয়েবলটা কি? পিক্সেল বা স্পেস, তাই তো? যেহেতু ইমেজটা আমার কাছে অ্যাভেলেবল, পুরো স্ক্যান করা ইমেজটা অ্যাভেলেবল, তাহলে যখন অ্যানালিসিসটা আমি করবো, ইউ ক্যান হ্যাভ দিস নন কজাল অপারেশন। নন কজাল অপারেশন হলো তো এক্সট্রাপোলেশনের জন্য ধরো করছি।
ইয়েস স্যার।
সো ইটস এ নন কজাল অপারেশন। অডিও সিগন্যাল নিয়ে করতে পারো, অডিও ফাইল নিয়ে করতে পারো, মোরলেস তোমার কাছে যখন কিছু স্টোরড আছে ডেটা, তখন তুমি এটাকে ইউজ করতে পারো। যখন স্টোরড আছে তখন তো ইন্ডিপেন্ডেন্ট ভেরিয়েবলটা টাইম না, এক্স ভার্সেস ওয়াই যখন স্টোরড আছে, তখন তুমি নন কজাল অপারেশনটা করতে পারবে, কিন্তু এটা ফিজিক্যাল একটা সিস্টেমের আউটপুট। Then only you can operate or you can have this non-causal operation. Otherwise, every operation will be basically a causal operation.
স্যার তাহলে যে সফটওয়্যার গুলো দিয়ে যে কোনো পুরোনো ছবি রিস্টোরেশন করানো হয়, তাহলে সবগুলোই তাহলে নন কজাল সিস্টেম?
না, নন কজাল সিস্টেম না, তোমার অপারেশনটাকে, সিস্টেমটা বলবো না, অপারেশনটা, এখানে তুমি সিস্টেমকে নন কজাল করতে পারো না, অপারেশনটা নন কজাল করতেই পারো, তুমি চাইলে করতেই পারো। তো আমার মনে হয় তুমি গ্রে স্কেল থেকে কালারে কনভার্ট করছো, তাই তো? তাহলে তোমার আরজিবি ভ্যালুগুলো সিলেক্ট করতে হবে। এবার তুমি করবে কি, একটা পার্টিকুলার পয়েন্টের পর গ্রেডিয়েন্টটা কিরকম সেটা জানতে গেলে কিরকম, ইউ হ্যাভ টু মুভ অ্যাহেড and see how gradient is changing, whether it is increasing or decreasing, and based on that you select the gradient for RGB, তাই না?
Yes, yes.
So it's a non-causal operation. You're moving ahead to determine what should be the scaling of RGB at this particular point, right? So it's kind of a non-causal operation, but it requires that the future information is available or stored.
Yes, sir.
But in this future information is not stored. বলো।
তাহলে তো এরকমও বলতে পারি যে যদি ইনপুট আউটপুটের ফাংশন যদি একটা সিস্টেমে অলরেডি স্টোরড থাকে বা আগে থেকে, তাহলেও তো সেটা হচ্ছে নন কজাল হয়ে যাবে। কারণ ধরুন y = xt স্কয়ার রয়েছে, তাহলে t = 5 এ কি আউটপুট হবে সেটা তো আমরা মানে আগে থেকেই জানতে পেরে যাবো। তাহলে তো
তোমার ইকুয়েশনটা বলছো yt
no xt এর হোল স্কয়ার স্যার, নট xt
এর হোল স্কয়ার। হ্যাঁ, কি করে হবে? তো টাইম তো টিতেই আসছে, তুমি t+1 এ যাচ্ছ না। হ্যাঁ, যদি বলতে xt স্কয়ার আছে তাহলে আমি ভাবতে হতো 2 হলো একটা 4, তাহলে নন কজাল। যদি ইকুয়েশনটা থাকে, কিন্তু ফিজিক্যালি কি সম্ভব?
তবে না 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 স্যার,
হ্যাঁ, তুমি না পৌঁছে তুমি ভ্যালুটা পাবে কোথায়?
হ্যাঁ স্যার,
তাই না? এটা তোমার অ্যাভেঞ্জার সিরিজ না, কিংবা ব্যাক টু দ্য ফিউচার সিনেমাও না, যে ফিউচারে যাবে কি করে, রাইট? এনিওয়ে, okay, so this is one classification, and last but not the least, the most vital classification is stable versus unstable system. Now, what do you mean by stable system? The stable system is one where the output does not diverge as long as the input does not diverge, or you can say, given a bounded input, output is also bounded. Then you call that a system a stable system. But given a bounded input, if output is unbounded, then you call it an unstable system. And this sort of stability that we are discussing here is called bounded input bounded output, or BIBO stability. So we can define the system to be BIBO stable or BIBO unstable. Now, how, in terms of mathematics, how it can be represented? Given an input xt which satisfies that mod of xt is less than equal to say mx, which is a finite value, that is less than infinity. Then if the output yt satisfies that mod of yt is less than my, which is again a finite value less than infinity for all t, then we say that the system is a stable system or Bibo stable system. And in case given xt bounded by mx, if the output is not bounded by any finite value my for any value of t, then it is called a unstable system. We'll give an example. I'll give an example. Each of these systems, linear, nonlinear, continuous, discrete, causal or non-causal, examples will be given. So this is the basic definition. Okay. So these are the classifications. Now comes the most important part. So we have been classifying the systems so far in different classifications, but these classifications are not independent. They are like interlinked, like this continuous time system can be linear or non-linear, right? They can be time varying or time invariant. They can be causal or non-causal, and they can be stable or unstable. And then not independently. They can be linear, time varying, causal, stable system, linear, time varying, non-causal, stable system, linear, time varying, causal, unstable system. So they're all like, and is all are basically layers of classification. A continuous time system may be linear or non-linear. Continuous time linear system may be time varying or time invariant. A continuous time linear time varying system may be causal or non-causal. Continuous time linear time varying causal system may be stable, unstable. So it's a complex set. Okay, have you understood this? So it's not that a continuous time system can only be linear or non-linear, or time varying or time invariant. It can be linear, time invariant, causal, stable system, or it can be linear, time invariant, causal, unstable system. So all the combinations that can happen by AND operation, but from each of the classification, it can either be linear or non-linear, time varying or time invariant, causal or non-causal, stable or unstable. It cannot take two values in a particular row in a horizontal distribution. It can take only one value, but it will take at least one value from each of these four classifications. Same thing applies for discrete time system. Have I made myself clear?
Yes, sir.
Yes, sir.
So in this course, follow.
Could you go to the stable and unstable slide again?
equal to xt plus x of q plus 1 এটা কি বলতে হতে পারে?
একদম ঠিক আছে। আমাদের in this course, sorry, we shall be discussing in this course on continuous time, linear, time invariant, causal stable. We shall be discussing in this course continuous time, linear, time invariant, causal, stable system. Obviously, in this linear time invariant systems are called LTI systems. And this causality and stability will have to determine in each of the cases. Right? So same classifications can be put up for discrete time system one by one. Discrete time, linear, time varying, causal, stable system. Right? In our course, we will be concentrating on only this continuous time, linear, time invariant, causal, stable system. In some situations, we may happen to encounter some unstable systems, but it will be basically linear time invariant system in continuous domain. Right? So now let us move on to some properties of the system now. First property will be memory, whether a system contains memory or it contains no memory. Now, what does memory mean?
RAM or ROM.
No. For a system, an output at time t depends only on the input at time t. Then we call that the system is memoryless. Like it depends on the instantaneous value of the input. But if it also depends on past inputs, then we say the system has a memory. I'll give you some example. Suppose as a first example, yt is equal to say 2xt minus x squared t whole square. So at any instant t, the output is a function of xt only. So it's a memoryless system. But what about this?
Memory system, sir.
Memory.
Because it depends on the past, all the past values of. So any integrator basically contains memory. Sorry. Okay. Say example C. I'll just write down here. Does it contain memory or not?
It's a memory system, sir. Memory system, sir.
Why?
Because a derivative means x of h minus x of minus h by 2h. When h tends to 0, then it needs the past values.
To calculate the derivative, that means you're trying to calculate the rate of change. So
Yes,
you should have at least the previous value. Then only you can calculate this.
Yes, sir. Yes, sir.
Just as a addition to this, I will just mention some of the discrete time system. The discrete time systems are represented by this. N is a sampling instant, an instant of the value at which it's obviously a memoryless system, right? But if you have something like yn is equal to xn minus 1, this is a system with memory, right? Now, okay, this is a system with memory. Now, can you tell me whether this system is having memory or not?
So
The
memory system, sir.
yn depends on the previous
Memory
value
আছে।
of n minus 1.
মেমোরি সিস্টেম বলছো তাহলে না মেমোরি লেস?
হ্যাঁ,
No, sir, memory
মেমোরি
system.
আছে।
আচ্ছা, কে বলছে মেমোরি লেস সেটু এ করো, রেজ ইউর হ্যান্ড। ছড়িস বলছো নাকি? কেন মেমোরি লেস কেন বলছো?
So memory কারণ স্যার ওটা কোনো মানে ইনপুটটা তো পাসের উপর ডিপেন্ড করছে না স্যার।
আচ্ছা, দেখা যাক। সরি, সবসময় থার্ড প্যারেন্থেসিসে লিখতে হবে এটা, হ্যাঁ। How can you represent yn minus 1 as? লিখতে পারি তো সরিস?
হ্যাঁ স্যার।
তাহলে করছে?
Sir, it will go until the initial value.
তাহলে yn minus 2 থেকে কি পাবো আমরা? এটাকে লিখবো x of, এটা নেস্টেড লুপ অনেকটা, তাই তো?
Yes, sir.
Yes, sir.
So this will continue, ultimately আমরা যেটা পাবো তাই তো? তাহলে মেমোরি আছে তো?
Yes, sir.
Right. So এই জন্যই do not jump into any conclusion, right? You just look at the what is hidden behind these equations, right? So it's a system with a memory, right? Okay. Next property, we'll move on to the next property. System is invertible or not? Now, if a system is invertible, if distinct input signals produce distinct output signals, or there is a one-to-one mapping between input and output signals, then we say the system is invertible. Like suppose example, yt is equal to suppose what's it, একটু কমপ্লিকেট করে দিই, cos t আচ্ছা, invertible বলতে বলছি given a particular input you will get a distinct output, okay, so that from the output you can infer what will be the input. There is a one-to-one correspondence between input and output, or one-to-one mapping between input and output. তাহলে বলতো whether this is an invertible system or not?
স্যার এটা নন ইনভার্টিবল, কারণ t এর মোর দেন ওয়ান ভ্যালুর জন্য cos t ভ্যালু সেম পাবো। মিন্স t is equal to 0 হলে cos t 1 দেবে, ফের t is equal to pi হলো 2 pi হলো cos t 1 দেবে।
Sir, actually
মেনি টু ওয়ান ম্যাপিং হচ্ছে
নাকি?
না না, অ্যাকচুয়ালি এক্সটিটাও জানতে হবে যে এক্সটিটা আমার 1 to 1 হচ্ছে কিনা, আদারওয়াইজ বলতে পারবো না।
দেখো, যদি এভাবে লিখতে পারি, if you can write like this, so if you know that given a particular xt it generates a particular yt, then you can calculate from that yt what should be the value of xt. So there is a distinct one-to-one mapping between yt and xt. So this is an invertible system. What you are saying that with respect to time, the parenthesis, the value within the parenthesis will change. That is the dynamics of the system. But the point is, those who have answered the last said rightly, that you need to find out whether you can express xt as a function of yt or not. If you can, then it's an invertible system. And if the expression yields a distinct value of yt, xt, given a particular y2, then it becomes an invertible system. It's an invertible system. Now, what is non-invertible? I'll give an example straight away. If this is a non-invertible system, right? Because say x1t equal to 1 and x2t is equal to minus 1. So both of them will yield same yt, right? So it is non-invertible. You cannot, if given yt equal to 1, you cannot determine whether x equal to 1 or minus 1, right? Similarly, for discrete time case, if you take the last example, it's also invertible because you can simply express xn as so it's a invertible one. Whenever you can find out this xn deterministically from this value or expression from yn, then it becomes invertible. But if you cannot find out deterministically, then it becomes a non-invertible one. Okay.
Sir, with x1t and x2t, are we using the inputs at different times, or it is
No, same. Same time. See, if this system is excited by an input x1t equal to 1, then the corresponding output will be 1. If you excite by an x2t equal to minus 1, then also the corresponding output will be 1. Right? So, if the output is given as 1, you cannot definitely say that the xt is plus 1 or minus 1.
Yes, sir.
It may be plus 1, may be minus 1. Whenever you cannot deterministically determine or deterministically obtain the input from the output data, then it becomes a non-invertible system. Right? The previous case, the confusion that was arising because of the Cauchy function. That's why intentionally I've given that. That is functional relationship. But you can, given a value of yt, you can find an expression of xt. Right? In terms of this time, when you are plotting the value of xt, then you will see a variation of xt with respect to time. That is what you have to find, the equation for xt.
सर पहले आगे कैसे होता है सर xt के प्लस माइनस रूट ओवर yt बोला जाए
प्लस माइनस रूट ओवर yt बोला जाए এবার প্লাস মাইনাস যখন তুমি বলছো you are actually mentioning two signals না plus y root over yt and minus root over yt, so there is not one to one correspondence. It may be plus root over yt or minus root over yt. It's not a unique signal, right? It should be unique. The relationship such that a particular output should be a result of a unique input. There should be distinct input and only one input that will generate that particular output. Then you say there is a one-to-one mapping, and you can say the system is convertible, invertible. Right? Okay.
Yes, sir.
Let us move on. How do you determine whether a system is causal or not? So I've already said that the output at any time depends on the input at that instant and all its past input, but not on future input. So in that sense, if I write down in discrete time domain, a discrete equation, it's a causal one. But whenever you write yn is equal to xn, it's not a causal one because it requires the information x of n plus 1, right? Similarly, in continuous time domain, if yt is equal to minus infinity to t x tau d tau, it's a causal one, right? Okay, what about this? Causal or non-causal?
Causal.
Why? There's a t plus 1.
But it is acting as a scalar at every point of time multiplied with xt.
Right. It is not related to input. It is some parameter that is a time varying. So this system obviously is a time varying system, right? Because if you apply same xt, if you apply at t equal to 0, it will give an result. If you apply at t equal to 1 or t equal to capital T, say 5 second, t capital T is 5 second, then this expression will change, na? It's a time varying system, but it's a causal system. Very good. বলো
স্যার বলছি সকাল থেকে স্যার ক্লাস করে যাচ্ছি, সবার নেট ফেট শেষ হয়ে গেছে, বলছে যে আজকে এখানে ইয়ে করতে।
তুমি কি বেরিয়ে যাবে নাকি?
স্যার আমি না
আরে 10 মিনিট লাগবে।
আচ্ছা আচ্ছা ঠিক
সবাই বলছে তো, হ্যাঁ 10 মিনিট হয়ে যাবে, 10 মিনিট হয়ে যাবে।
ঠিক আছে
ঠিক আছে। Okay, the stable system have already defined that xt is such defined that mod of xt is less than mx. Then if yt is such that mod of yt is less than my, with mx and my being finite, then the system is stable. So see, let us see how the system stability can be defined. So as an example, say your system is yt is equal to t, whether it is stable or not. So first of all, you consider a signal xt which is bounded by a finite value b. Then your mod of yt will be mod of I'll go through it very quickly so that you can understand. Don't have to wait. So you can write that less than equal to this. Now, given that expression for boundary for xt, this is typically less than 2b square, and this is less than b. This b is finite, so this is also less than infinity. So the output is bounded, so it's a stable system, right? Or a bivostable system. Right? Now let us check. We have already derived an equation for a discrete time system in this form. Oh, sorry, minus infinity to 10. Okay. So whether it is stable or not. For that, let us choose a bounded input xn to be a step function so that mod of xn is bounded by 1. So it is bounded. So what about mod of yn? Let's take mod of this limit, and xn is un uk, k is equal to minus infinity to n. Now what is the value of uk? Uk is nothing but un is defined as n for the range less than infinity. So first of all, what you can omit is this minus infinity term, and since it is 1, so mod you can omit, so it will be k equal to 0 to n. And what is the value of uk at each point?
1.
Bounded by 1, so it will be bounded by 1, right? And this boundary can be calculated as n plus 1. So mod of yn is bounded by n plus 1, or you can say, I'll write it here, that is less than equal to n plus 1. Now you tell me whether yn is bounded or unbounded.
So unbounded.
Unbounded.
Right. So as n tends to infinity, it is unbounded. So this system is basically an unstable system.
স্যার তাহলে যে কোনো সিস্টেমের স্টেবিলিটি চেক করার জন্য কি আমরা ওই ইনপুটটাকে স্টেপ ফাংশন দিয়ে তারপর আউটপুটটা দেখে বুঝে নিতে পারি?
তুমি যে কোনো ফাংশন দেখো, yes, yes, but it should be bounded. Any function that is bounded, that magnitude is bounded.
আচ্ছা আচ্ছা।
Okay. So this is how we can determine the stability. So last but not the least, last two parts are remaining. I will go on very quickly. যেটা নিয়ে অনেকের তোমাদের কনফিউশন আছে, time invariant. Okay, so the condition is that if xt yields yt and x t minus t0 yields yt minus t0, then it's a time invariant system, right? Example, let us check. Yt is equal to sine of xt, whether it is time invariant or not. So first you will take an input t, which is x t minus t0. Corresponding output will be y1t, and so therefore y1t will be sine of x1t, that is sine of x t minus t0, corresponding to this input. Now we have to ensure if the system is time invariant, then y1 t should be equal to y t minus t0. That is, if we change the input, shift the input by amount time t minus to t minus t0, then output should also get shifted by this. We have to prove this. Just put in this expression t minus t0 in place of t. So what you will get? So obviously, this is nothing but y1t. So it's a satisfied. So y1t is equal to yt minus t0. So it's a time invariant system. বোঝা গেল? y1t is output due to the shifted input, and that output is same as the output shifted by same time delay as the input is shifted. So the entire nature of the output is retained. Okay. So I'll give you an home task. You have to show us. Okay, I'll not give you a home task. That is, I think you're quite quick to catch up. Okay, do not rather than this. Let us say in this case your yt is equal to t sin xt. Then what happens? So given an input x1t, the corresponding output it yields is y1t, and that will be t sin x t minus t0, right? Now y of t minus t0, what will be this?
The shape changes.
Yes, so obviously in this case y1t is not equal to y t minus t0, so it's a time varying system, right? So this way you can find out whether a system is time varying or time invariant. So I'll conclude this just a minute. Whether a system is linear or not. So if you just see whether a x1t plus b x2t yields a y1t plus b y2t, where x1t yields y1t and x2t yields y2t. So if you can satisfy this, then it's valid. Now I'll give you an example. X squared t, suppose. Then you define an input x1t, so that one give you y1t is equal to x1 squared t, x2t.
This is non-linear.
Yes, this is non-linear.
Sir, as we are
Show you
squaring,
how
and
it-
squaring is a non-linear operation. From that, can we say that the result will be the
Yes,
system
it
will
is
be
right.
non-linear?
But you can rightly straight away write that. Straight away. The squaring, cube, any power is a non-linear operation. So what will happen? So if you have this x1 t plus x2t, from that what you get? You get x1t plus x2t whole square, whereas your y1t plus y2t yields x1 squared t plus x2 squared t, right? So your yt or this due to y due to x1 x2t is not equal to this. So this property is not valid. So it's a non-linear one. In some situations, what happens? Okay, this was clear. There is the x squared term. In some situations, what happens? Due to the some of the hidden terms or hidden relation between the equations, it's very difficult to judge whether it's a linear or non-linear, since it's obvious. So it's better. So you go through this check. Okay. In this case, it was quite obvious, right? X squared is given, so it's a square term, so it will be a non-linear. Okay. So okay, as we already crossed a lot of time, so I'll stop here. So if you have any queries, you can please ask.
Sir, any book?
It's very difficult. Basically, I have some handwritten notes that I have captured from different books. One book you can follow, since it's a part of a control system engineering. There are two books one by K. Ogata, which is called Modern Control Engineering. In this book, in the first 2-3 chapters are dedicated for the course that we will be taking up. That is the mathematical background, derivation of mathematical model of physical systems. There is also a book by Kuo, which is termed as Automatic Control Systems, if I'm not wrong.
Benjamin Ko.
Huh?
Benjamin Ko.
It is BC. Yes. Benjamin Ko, BC Ko. Not FF Ko. In circuit theory, we have FF Ko. It is BC Ko. Right. So it's like automatic control system. So you can consult either of these books. And I will try to provide you with intermediate notes. As soon as I cover up a portion, I'll give you some notes. Okay. So as far as classification and properties of system and definition of systems is concerned, this portion is covered. So I'll make a classroom. I'll create a classroom and then upload the note over there. Okay. And I will send request to a group mail so you can join. Okay. Okay. Thank you then. I'm stopping here today. Okay.
Thank you, sir. Thank you, sir.
Thank you, sir. Thank you, sir.
Okay.